All right, everyone, welcome, and thank you again for attending. Thanks for those online as well. Today's speaker is Dr. David Roueche. He's an associate professor at Auburn University, and Dr. Roueche's work is primarily in resilience, resilience of light frame, low rise, and even some mass timber structures. He's also done a whole lot of post-event reconnaissance after hurricanes like Irma and Harvey, as well as tornadoes like that in Joplin. And others. And so Dr. Roueche is going to talk to us today again about resilience and specifically timber structures. And so welcome, Dr. Roueche.
Awesome. Thank you, Michael. And thank you all for coming out for this. It's good to be here. Was back here in, when was that? June of this year. Saw the campus for the first time and really enjoyed it. So good to be back here. As you mentioned, I'm from Auburn University, the other Tigers, one of the other Tigers, except for we're a little confused. We can't figure out if we're Tigers or War Eagles or whatever it is that we are. We're just, yeah, we're just all glad that we're not elephants. So we'll leave it at that. All right, but as he mentioned, my background is sort of spans wood frame and timber structures, but a lot of it and my work is involved more on extreme windstorms, hurricanes, and tornadoes, and their impacts on communities. And so I'm kind of bridging the gap here. We've also done quite a bit of work recently in mass timber structures as well under different loads. And so we'll try to blend all this together. Don't worry, there's not a whole lot of, I don't know if I have any equations here. There's a few numbers, but lots of hopefully interesting pictures and videos to walk through timber to the extreme. What happens when timber gets exposed to those worst cases, ultimate loads that we designed for. So I'll start off with, here we are in this room. I'm assuming most of us are advocates for mass timber and timber buildings. And so I'll just show first here a few examples of some timber structures here in Auburn that we're very proud of, and a few others that just highlight why it is we love this material so much. And so this is the Heyday Market and the Culinary Center right next to it that Auburn opened up in fall of 2022. Beautiful building. Blue lamb columns, CLT ceiling, and this is what it looks like right now on the inside with a whole lot of different shops, and they use this in different ways for different students operate a lot of the spaces, and it's been a very popular hangout spot since it opened up. The beautiful building. I would also highlight something near and dear to our heart. This is the admin wing of our Advanced Structural Engineering Laboratory. So this opened in summer of 2021 and was actually the first mass timber building on our campus. And so we take a special pride in that it was a part of our Advanced Structural Engineering Laboratory. And as part of it, we had a mass timber building, we had a steel building, we had concrete, kind of a back wing. So we tried to represent all the different materials under one building. And so this is the outside of it under construction, CLT ceiling, glulam beams, and then heavy timber columns. And this is what the inside of it looks like. This is our grad student spaces, and it's just a very open, inviting, great collaborative space to work in. And of course, very proud of this building as well. And then I thought I'd just highlight a couple others that I've really enjoyed that you all should be familiar with. So of course, we have the Andy Quattlebaum Outdoor Education Center. I really loved being able to visit that over the summer, and it just looks like a fantastic spot. My only disappointment was that I wish I'd brought some stuff with me, had some time to go out and take some kayaks out and enjoy that space. It looks like a wonderful resource. But I also want to call attention, with all of that's going on in mass timber, and it's wonderful. It's really expanding the market for timber. Let's not forget about the low-rise single-family home. These still use, I was doing some rough calculations this morning. I mean, about 18 million tons of lumber each year go into white wood frame. So there's still a ton of market for this. It's growing. Excuse me. It's necessary to maintain affordability of our structures and provide for affordable housing throughout the U.S. and really around the world as well, which is such an important concept as we adapt to climate change and just everything else that's changing in our world. And in that, I'll throw a quick plug in here for the Rural Studio for our architects. Probably may be familiar with this. Rusty Smith and their team do such a fantastic job doing kind of low income, affordable housing, and doing just a great job with those designs. And this is a necessary part of it in the utilization of wood in many different structure types. But I want to turn our attention, as we think about, yes, we can look at timber and we can see sort of the benefits of it and the affordability and the aesthetics of it and appreciate that. But how do we sort of formally capture, well, just how much more beneficial, say, timber is than these other structures? And so some of you may be familiar already with life cycle assessments and that process. It sort of used to be more restrictive, but it's becoming more and more common even in engineering to do these life cycle assessments. And so if you're not familiar with it, basically it's a way of tracking from material, kind of raw material, which in the case of wood, you're talking about forest management, all the way through the processing of that material into actual building materials, and then into construction aspects of it, and then into the use and repair and maintenance of it, all the way to end of life and the deconstruction and where does it go afterwards? Is it a landfill? Is it recycled? And so on. And so these frameworks, and there's lots of different ways sort of the details of these come out, but these life cycle assessments allow us to holistically capture the entire system and be able to compare between, say, timber, mass timber and steel and concrete, and look at things like, well, what's total embodied carbon or total, embodied energy and things like that over the entire lifespan. What I want to highlight here is kind of notice up here, it's a little bit small, but up here in the top right, a lot of these assessments are done making it some assumption of what the lifespan of the structure is. And typical lifespans may vary, but oftentimes it's somewhere in the 55, 60 to 75 year. What we assume is the lifespan for our structures. And so we work these sort of cost benefits and holistic assessments off of this normal use and normal life cycle. What I want to talk about today, though, is what happens when something comes and these extreme events we designed for come and interrupt that life cycle. And we're talking now about sustainability, and we're talking about and quantifying sustainability over the course of 60, 75 years. What happens when 5 years into the use of the building, the extreme event happens? Okay, and the extreme event could be a tornado. I may show my age here. It could be something really extreme and be the ultimate unprecedented Sharknado that comes through. You never know. Things change. Which I don't know how many. I may be showing me how many people have ever actually seen Sharknado. We use it. Okay, there's a few brave souls out there willing to admit it. All right, I have not. I've seen clips. That's as far as I'm willing to go with the amount of time that I have. All right. So anyway, something like that happens. What happens afterwards? Unfortunately, too many times, and this is what I started my graduate work on, it looks like this afterwards. And these affordable, these timber buildings, white wood frame especially is sort of gets this bad rap for, okay, yes, it's great, it's affordable, it's easy to construct. Then the event happens and now it's all scattered all over the place. And this is sort of the reputation that's out there for stick frame buildings. And I see this time and time again after a tornado, after a hurricane, people, the media tends to focus on the damage. And then you get sort of all the public opinion that's like, why in the world are we still building with stick frame? Like, why haven't we outlawed that yet in tornado-prone regions and things like that? That sort of conversation. And so one of the things I want to, that I've done as part of my career, both in grad school and I continue to do it now, is doing lots of these assessments. And they go out after, it's probably been 30, close to 40 now, different hurricanes, tornadoes that have gone and done these types of assessments afterwards, looking at what failed, why it failed, what can we do better, what can we learn from it, and trying to turn this into actionable data that we can learn from and use. But I'll extend this a little bit further, and let me make a quick point first before I do that is, you see all this debris and we talk about sustainability, that's not sustainable. Okay, so this is from an event like the Joplin tornado, but this is the Army Corps of Engineers sort of put this graphic together, and it looks at basically the amount of debris that was generated by the Joplin tornado. So a total of 3 million cubic yards. The vast majority of that was from timber buildings that were destroyed, and sort of the contents and all from that. And so 1 million cubic yards is basically enough to fill a football field 510 feet high. So you talk about 3 million cubic yards of debris generated by a tornado like this. And all those benefits that we have, the carbon sequestration and all that, now it's in a landfill somewhere, or it's being incinerated and so on, and we're losing the benefits of that from a sustainability perspective. So the takeaway here that we'll sort of touch back on at the end of the presentation is that we can't talk about sustainability without also talking about resilience. In my mind, those are those are completely linked, and we can't have one without the other. And so resiliency, there's many different ways of defining it, but I'll use the National Academy's definition here, which is the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse events. And certainly with, you could say climate change and our hazards sort of changing through that. You can also simply just look at the amount of how our exposure, how we have growing populations in vulnerable areas. With the growing population here in the US and around the world, what does that become? That's more targets, if you will. Even if the hazard were to stay the same, there's more risk out there that we have to adapt to, be able to absorb, and be able to recover from. So if you've worked in the area of resiliency at all, you may be familiar with what we call the resilience curve. How many of you have seen this before? Resilience curve? Okay, just a few of you. So we'll walk through it. So the resilience curve basically looks at here on define our axes first. So we have kind of capacity or functionality here on the y-axis. And then on the x-axis is time. And so before the event that happens, we have some baseline functionality, some baseline capacity, whether it be to a building or a community as a whole. And these can be at different levels. Not every community is the same. We all operate at different levels of functionality and capacity and so on. And then the event happens. Again, tornado, earthquake, hurricane, sharknado, whatever it is that happens. And there's some decrease in capacity that happens right away. And then you have the mobilization as the recovery efforts start to begin. And we're understanding, okay, what was damaged and what resources do we need, first responders and all of that. And then we start that recovery process and then eventually reach a new normal. And every community is different. We sort of measure this idea of there's different ways of measuring resiliency. You can sort of measure the area under the curve here as some measure of how long does it take the community to rebound to a new normal and reach this new equilibrium state. And some communities, like the one shown kind of illustrated in red here, may have a significant drop from that hazard and may never fully recover to what they were before. Industries may move out. You lost a school, families move out because they have to provide for the education of their kids and things like that. And so communities may never recover. And so resilience, being able to understand that both on an individual building scale and a community scale is of utmost importance if we're going to talk about sustainability and talk about having communities that are sustainable in years into the future. So if we're talking about resilience, then let me also try to, again, big picture. Engineering students in here hopefully are somewhat familiar with this. When we talk about resilience, we're not just sort of grabbing making a shot in the dark of, well, we need to design for earthquakes, or we need to design for tornadoes, or maybe we do, maybe we don't. No, we have minimum baselines, minimum requirements that every building in the United States is designed for. And so these come from ASCE 7, minimum design loads for buildings and other structures. And so what I've shown here is just a seismic hazard map for some typical conditions, typical buildings. And you can see kind of the hot spots that are highlighted here. So obviously these sort of purples out here, that's where we get the majority of the earthquakes. That's where your higher loads are going to be. So you're not going to design a building, in where I'm at in Auburn, Alabama, somewhere over here or down in Florida. You're not going to design it for the same earthquake levels as you do in California. Okay, the risk is not the hazard risk is not the same. We do similar for hurricanes and wind. So this is our wind design maps. And you'll notice here, unsurprisingly, that most of the kind of high design levels are near the coast where we have our hurricanes. But notice that our interior here for typical buildings, it's some really low wind speeds. What about all the tornadoes? Well, currently, as of ASCE 722, there are now some provisions for designing kind of category 3, category 4 structures for tornadoes, but we still ignore tornadoes for everything else. And so what that means, show here, highlight some of Dr. Peng's work as well, but this the figure on the left is all the tornadoes that have occurred since 1950, according to the National Weather Service. On the right is sort of an annual probability of any particular point being struck by a tornado, at least EF2. And we're right now ignoring all of that hazard in our typical building designs. We don't consider tornadoes because of the low probability, because of some of the uncertainty in the loading and so on. And so when you talk about resiliency then and sort of what our design levels are, how our buildings perform, what can we do then to make our buildings more resilient? And so I'll put in a quick plug here for the STEER network. So I'm an associate director of this. It stands for Structural Extreme Events Reconnaissance Network, funded by the National Science Foundation in 2018. And we've been going really all over the world doing post-disaster kind of reconnaissance efforts, building the capacity of the community to respond to disasters, earthquake, hurricane, tsunami, et cetera, and also developing standardized data sets from these. So for example, here's the 58 different events we've responded to so far. It includes hurricanes, Michael and Idalia and Ida, different tornadoes as well. Some of these are virtual responses. Some of these are in person. And as part of these responses, particularly the field responses, we collect lots and lots of data on how different buildings perform. And we'll do this in a number of ways. We may have performance assessments that are just in a smartphone kind of app, a survey that we're filling out for each one. We utilize street view cameras, kind of surface level panoramas, as we call them, drones, and all sorts of other technologies, essentially freeze the disaster in its place, capture as much data as we can, and then try to learn from it later. So when we collect all this raw imagery, then we can sort of combine it, synthesize it through GPS to get a complete picture of the disaster. This perishable data, maybe link it to the hazard, link it to other building attributes and characteristics of it so that we have a standardized database of building performance after disasters. And so we've been doing this, like I said, since 2017 for me personally, and then STEER kind of came along in 2018 to formalize a lot of this. And there's lots of data that we can have now to look at how our buildings actually performing. And a lot of these are wood frame structures that we've been looking at. And I'll put a quick note in here that all of this data is also freely available. It's on the NSF Design Safe repository. If anybody wants it for train some machine learning model on or do any sort of modeling aspect, there's a lot of good data out there for you to use. If you'd like to know more about that, let me know afterwards. But I want to talk next, though, about okay, what are we actually seeing from all of these assessments that we've done? Basically, 6 years or so of 7 years of doing these standardized assessments. And so what I'll do is I'm going to show a plot here in a second that talks about what we call component level building damage. So looking at percentage of roof structure, roof substrate, roof cover, wall, et cetera. And all we're talking about here is things like roof structure is sort of your main rafters, trusses. Roof substrate is your decking or your sheathing. And then the roof covers, your asphalt shingles or clay tiles or things like that. And so this is a summary of about 4,000, almost 5,000 buildings. In this case, these are all light wood, or almost all light wood frame residential structures. And so point out a couple of things here. On the y-axis here of what we're showing, this is basically it's called an empirical fragility function. It's basically looking at what's the probability of experiencing, say, in orange, at least 25% of the roof structure has been destroyed by the hurricane or the tornado. And then on the x-axis is the wind speed in this case. So as we increase in wind speed, we would expect to see a greater probability of experiencing, say, at least 25% loss of the roof structure or 50% loss of the roof cover, et cetera. Okay, so it's linking damage to the hazard itself. And so one of the things that you'll notice is, I said earlier that we ignore tornadoes in our design. Well, guess what? As our wind speed increases, what do we see? We see lots of damage, or damage increase significantly with tornadoes. Notice what we see in hurricanes, though. If you focus on the top right, looking at roof structure, really that structural failure in hurricanes, even as our wind speed goes way up, we really very rarely see structural failures in hurricanes anymore. And when we switch this to modern, what I call modern buildings, so homes built to what I call International Code Council, so kind of IBC, International Building Code, about 2002 and on. This is normalized now. The x-axis here is the estimated wind speed, peak wind speed that the home experienced, divided by the design wind speed, so that we can kind of account for not everywhere in the US has the same design wind speed. And what do you see here actually is even more pronounced. In our modern buildings, other than Hurricane Irma was kind of an outlier, and that's where you see some of these low values or some of these a little bit of damage in some of the lower wind speeds. But other than that, in new buildings, we just don't see wind failures in hurricanes. And these are stick frame buildings. They do just fine. Okay, so when we put the engineering into it, we connect them properly. When we design them properly, it's a fantastic solution. We don't need to move away from it. We just need to design them properly. But if I go back real quick, but you also notice that there's all sorts of odd things kind of going on with roof cover and roof substrate, and how there's quite a bit of variability. It's not always this sort of nice monotonic relationship with wind speed. And so as part of my NSF career project, we're trying to more holistically look at this and say, hey, when I look at an individual building and look at why one performed one way and one performed another, what are all the factors that go into how one building performs compared to another? And here I've kind of broken them up into sort of a bell curve, if you will, of load versus resistance, right? And a lot of times in your undergraduate studies, you may be looking at it as a deterministic. You calculate exactly what the load is, exactly what the resistance is. In reality, it's probabilistic. We don't know exactly what the load is. We don't know exactly what the resistance is. The intersection of those, when our load is greater than the resistance, is when we get failure. And there's all sorts of factors that come into whether a failure occurs or not. And things on the hazard side, kind of terrain. This is more so, of course, focused on wind, but the hazard itself, duration of loads, what type of storm it is, and then the upwind terrain, the aerodynamics of the structure. Is it one story? Is it two story? Is it a gable roof? Is it a hip roof? Then you come down to the resistance side, and you have all sorts of different load paths that you can configure, and what connection are you using, and what species of wood, and that all plays a part in driving these sort of large variabilities that we see in performance. And so we're trying to unpack some of this. And so what I'll show you is just a few things that we've learned that are kind of practical, but tied to light wood frame construction and being more resilient and for tornadoes, hurricanes, and then there's applications to earthquake as well. And so one of my PhD students has been working on is sort of idealizing the entire load, what we call the load path of a typical home, into a chain, what we call a load chain. And so if you walk down kind of a typical load path, you've got your rafters and you have your roof to wall connection and double top plates and sheathing and studs. And then you come down to a bottom plate and joist. And then it may either be on a slab, a concrete slab, or it may be on a masonry stem wall. There's lots of different ways that we can come up with these different load path configurations. But he's essentially worked together, okay, which ones are in parallel, which ones are in series, and sort of idealize this as a chain. And so a little thought experiment here before we go too much further. Which chain is stronger? What's the strongest chain? Okay. I have a vote for the top one. Okay. Any other thoughts out there? Are you? We should limit it. No professors can answer. Just kidding. All right.
Deterministically or probably?
Well, look at the variance of the two. No, so in a simplistic version of this, a chain is only as strong as its weakest link. So while it may, we have like some jewelry chain. Sorry, I'm putting the wrong one. If we have some, maybe we look at, did it disappear on me? All right, so at the top, we just have a gold jewelry chain. All right, not very strong in and of itself. Now we've placed this really large, strong, steel link in the middle of the jewelry chain. But is that link going to do any good? It's just going to find a failure somewhere else. And what most of our wood frame, especially light wood frame, kind of prescriptive designed or prescriptive built structures are sort of, I don't know if this will work or not. It's lost on me. So this one at the bottom, this is what most of our, if I could idealize most of the construction that I see when I go out and do these assessments, it's in the bottom. You have an anchor bolt, which has a ton of strength, and then the next link in the chain is some really weak connection. And so you just have these very disproportionate strengths that are all sort of strung together, and we're only as strong as our weakest link. And so wind is simply looking through it, finding the weakest link, there's the failure. And so let me identify just a few of these for, again, just to kind of ground it in reality here with some practical things. So to start with, excuse me. start with, here's a home, one of the first ones that I actually looked at when I came to Auburn. This was like a week after I started my faculty appointment at Auburn. Was out in the field in Rockport, Texas, doing these assessments. And this is a home built in, so Hurricane Harvey was in 2017. This was really still under construction. It was just about to be moved into, they hadn't finished up the interior yet. But when we saw this outside, I was like, man, okay, sustained a lot of damage. Looked inside, and man, they've got straps everywhere, right? I mean, we've got our roof to wall connections. There we go, back now. So we've got roof to wall connections tying our rafter to the top plate. We've got the top plates tied to the studs. We've got a brace garage door. We've got, again, all of these straps everywhere. Look down at the wall to foundation connection, straps all over the place here. We've got anchor bolts, 1/2-inch anchor bolts at 6 foot on center. We've got oversized washers. Like, we saw this like, okay, this looks like, this is what we're telling everybody to build like, and it just got demolished by a hurricane. What's the problem here? So a little forensics, and here's the failure sequence. One, it was in a construction site. There's lots of debris flying around from kind of loose construction. On the front, if I can jump back real quick, so there's this smaller garage door here that a piece of large debris impacted. So it impacts that large garage, or that garage door, that creates a large opening. Essentially, the wind enters that opening, pressurizes the interior of the building. Wind is going to find a weak link. And what was the weak link? Up at the ridge, where all these rafters come together at the ridge of this roof, no straps, no anything. It's just sort of toenailed into the ridge. So what happens? It sort of peels up there. As soon as it starts to peel up, wind catches it, flips the whole thing over, and now you've lost your roof. So all of these straps that were there, I'm sure they demolished the house, had to start over again. Okay, where it found the one weak link in the structure. And so what I've been trying to do in a lot of our assessments recently is trying to model and identify in the field these common weak links that we're seeing. And so I'll highlight a few of these. So to start with, up at the top, the roof sheathing or the decking, kind of the top of the load chain, if you will. In order of increasing capacity, there's a number of things that we can do that go from weak to strong. So we could have the fastener spacing. So 612 means it's essentially 6 inches on center on our edges, and then 12 inches on center in the middle part. We could increase that to 6.6 in some coastal areas, and maybe even 4.6, where they're 4 inches on center on the edge, and then 6 inches on center in the middle, or the field region, as we call it, of the decking. So increase capacity as we increase the number of nails. We can also change the fastener type. So a lot of older homes, you might see staples, really not a good way of doing it. Common nails or smooth shank nails. Deformed shank, which are kind of ring shank or spiral shank, those are really good. And then you could have screws as well. And I'll show some differences between the capacities here in a second. And then lastly, you can increase the length and diameter. All of these will increase the capacity. So to give you an idea, so if we use a smooth shank nail, a 4D nail, which I've seen in a number of buildings, typical 612 spacing, we get a mean resistance. So basically, how much wind pressure would it take to fail that panel? About 40 PSF, which is kind of in the EF0 tornado range. If we keep the exact same spacing and switch to a ring shank nail, we're up to 170 PSF in an EF3 tornado. Same spacing, there's really no cost difference in either. We're just switching to a deformed shank nail, and boom, we jumped up the capacity. What is that? Almost 4 times. But then, of course, you have, that's our nice, here's what it should be. And then you have the real world, right? So in the real world, what happens? So you get lots of what we call shiners, where they miss the nails. We saw this. This is in Araby back in 2022. Some missed nails. You have a lot of nails that are really close together, ended up splitting the sheathing and creating a failure point there. We also had here on the far right where they basically overdrove the nails. So where they're using a nail gun and the too high of a pressure on it, and it's basically shooting through half the panel as it's going into the wood, and now the panel just sort of pulls out around the head. So all the nails are still stuck in the wood, and the panel just sort of breaks out around it. So you should have 150 PSF of pressure, and you're probably only getting, from a modeling, you may only be getting 100 because you're compromising the structure. This is Rolling Fork, Mississippi. Some of you may have heard about this one earlier this year. apparently a lot of shiners or missed nails because there's entire rafters with no nails. Panels are gone, no nails in them at all. So this is kind of the real world. Roof to wall connections. This is perhaps the most critical connection in our light wood frame construction, because if you can keep the roof on, that helps hold the walls together. It helps provide life safety and so on. So there's lots of ways you can do this connection, but what are we seeing here? So in a lot of our older buildings, we're still using toenails, which is just using these sort of angled or inclined nails. You can do it this way. It's not a great way of doing it. I'll show you again capacities here in a little bit, but they'll maybe put them too close together, split the wood, or not have enough. Or again, you're limited in the capacity you can get there. Or there's things like, again, going back to the Rolling Fork, Mississippi tornado earlier this year, they're using a strap or a clip, I should say, of some kind, but it may be a little bit hard to see, but there's one nail up in the top left, and that was it. Now you might say, but hey, it still stood, right? This was further away from the path. These are all very similar homes, and all the ones closer to the tornado path completely wiped out. Okay, this was just sort of evidence of what type of construction they were using, and as you can tell, pretty poor construction. Here's another example. This is actually in Florida from after Hurricane Irma tornado. They, again, used hurricane clips and attached it to the upper top plate, but didn't have any connection between the upper and the lower of the top plates, and it just failed at that level. And so you've got all the rafters failed, and it just took the upper top plate with it. A very weak connection, which again, I'll show in a second. This is from the Mayfield tornado in 2021. Same thing, used hurricane clips, and our lower top plate still stayed in place, and the rafters or the trusses just failed and pulled the upper top plate with it. All the hurricane clips still attached to it. Just found the next weakest link. So to give you an idea, so here's sort of the average ultimate capacity of some different configurations. So here's just 3 toenails, which is a very common practice in a lot of the older construction. You get about 400 pounds of resistance. All right, now 400 pounds sounds like quite a bit. Anybody squat or bench 400 pounds? Brandon? All right, Brandon can do it. Okay, that's pretty impressive if you can do either. Bench certainly, if you can squat even that much, you're doing pretty good. So it sounds like a lot. An EF2 tornado is going to apply thousands of pounds of force to a typical home like this, given the size and spacing and so on. So we need stronger connections. We can use an H2.5, and as long as the sheathing overlaps both top plates, provide that continuity, you get about 1,750 pounds. But jump down here real quick for sake of time. If we use a hurricane strap, but we don't link the upper and the lower top plates together, we only get 540 pounds. So we get a little bit of an increase over a toenail, but we've got a lot of capacity there that we're wasting because we're using this really weak link to connect everything together. So here's an example of that. So here's on the inside, you may use H2.5 that just barely kind of catches in between the upper and the lower top plate. And then on the outside, the sheathing just catches the lower top plate. So you've got a failure point in between those where the wind just picks it right up there. Same thing happens at the floor level where you have the walls. They build them in sort of 8-foot sections, stand them up, run the sheathing on them, and you get this weak joint in between, a fuse, if you will. Failure, entire wall comes down, roof comes down, life safety risk, all of the above, becomes a bunch of debris going into a landfill. A couple more just quick things here. So roof to wall connections. This is perhaps the most important connection for life safety. And there's all sorts of different configurations here from, this is in Tuscaloosa, where you just have wood frames stuck on empty cinder blocks, no positive connection there whatsoever. Tornado picks the home up, throws it. Huge life safety risk. Then you get cases like this where you've got, a grouted cell every 16 feet, but no nut, no washer. Okay, again, you've got a lot of capacity in that anchor bolt, but the next weak link has very little capacity. And so as a system, you have very little capacity. Or things like this from Nashville, Tennessee in 2020, where you've got anchor bolts stuck into the head joint of a cinder block, and in these tiny blocks here where you've got all the capacity in the steel and you're not really using any of it. Or you get things like this. This is again from the Rolling Fork tornado, where now, okay, we've got an anchor bolt that's going into the concrete. Now our wood is splitting around it. What's going on here? Well, we're using this tiny kind of 1-inch washer here. And I know I don't know if anybody's from your wood design class in here, but if you can imagine in this case up here, if the load is being transferred to our bottom plate through our sheathing, and we've got an anchor bolt here, what's going to happen, switch to, what's going to happen is we get essentially tension perpendicular to the grain in this bottom, in these extreme fibers. Wood is extremely weak there. And so we get this it just snaps up and breaks. And so if we use a 3-inch square washer that extends the bearing over the entire surface, you get a, drawing a blank on the word, I'll come back to it. But so it extends so we don't have as long of a moment arm, we don't have as much stress here at the bottom, and it's a much, much stronger connection. And so again, similar thing here. If we can use 1/2-inch anchor bolts, 6 foot on center, and use that 1.5-inch round washer, even with the wood sheathing overlaps, and we got about 180 pound per foot of capacity. If we use a 3-inch square washer, we're almost over 3 times that capacity, just by switching out a washer. So they have these little things, structural fuses that go all throughout the load path that we're trying to identify, develop the modeling for, to be able to analytically show exactly the benefit of these things and improve education and the resilience of our communities. But because of these and many, many, many more, how am I doing on time? Ooh, I'm almost out of time. Okay, run through this very quickly. So because of these and many more, what we end up getting is things like this, where you have a community in Panama City where you've got lots of damage sort of throughout, many homes with roof structure damage, others that are doing okay. And then you've got communities like this that look almost just fine after the hurricane. And then we come back and compare, these communities are right next to each other. They saw the same wind speeds. Ones are built properly, proper load path, attention to detail, engineered, the others aren't. You see very, very different damage patterns. And so I'll just show show one or two. I'll skip through some of these. So 1 or 2 quick videos here. So this is, many of you may be familiar with the IBHS. It's a massive wind tunnel facility. They can put 2-story buildings out in front of and put hurricane winds on them. On the right was their sort of fortified construction that uses a continuous load path, engineered load path. On the left is sort of a bare minimum kind of old construction techniques. Obviously different performance. How many of you would want the home on the right? Okay, I think we would all agree there. All right, it's not just wind. I've talked mostly about wind because that's my background. But we can design resiliently for earthquakes as well. This was some large-scale shake table testing done in Japan, 3-story whitewood frame structures subjected to some very strong earthquakes, and you see lots of movement, lots of shaking. Yeah, there's some little deformations and so on, but performed great if we connect everything together properly and engineer. I'll show all of this, but this is some recent testing. This is glulam CLT, the tall wood project that an NSF project is being done now, doing a 10-story mass timber building. And again, performs extremely well under earthquake loading. And it's not just wind, not just seismic, but there's also blast. We've been doing some work now, and this wasn't our work. This is earlier work done on CLT under blast loads being used in military applications. And this is sort of obviously a very slowed down version of that. And you can see the deformations, you can see a little bit of damage, but it performed extremely well. The CLT did to the blast loads. And so we've got a project right now in our Advanced Structural Engineering Laboratory that's developing this further. We're getting a high rate UTM to be able to test timber under a wide range of strain rates, controlled manner. There's again, lots of different ways to do resilience. But here's steel timber composite floor system, some work we're doing there, replacing the concrete floors with CLT, actually tying them together with the steel as a composite system. And as we look at the performance of this, here's where if you just put a CLT slab on top of the steel with minimal connection between them, you'd be a capacity of about here. By actually using screws, it's 12 inches on center, we jump all the way up to here in our capacity. So there's a lot, and then in terms of the LCA benefits of that reduces the mass, it reduces the embodied energy, and so on. There's a lot of indirect benefits to this as well. So it all comes back though to here, which is, yeah, we can come up with lots of innovative ways and fix all these, but it all comes back at this point, you've got to remember what is our minimum design level, and if it's a rush to the bottom, a rush to just meet that minimum standard, we're not going to be a very resilient community. And so as a community, as engineers, as architects, we have to decide, okay, where do we want to be in this resilient curve? Not just the everyday use, everyday operations, but when an extreme event happens, how do we want our structures to perform? And build that into our thinking, build that into the life cycle assessment, and choose resilience. So with that, a little bit of a rush there at the end, I'll leave it here. And again, this is sort of how I view sustainability and resilience. And that Venn diagram, resilience is just one part of sustainability. So sorry for going a little bit long there. Thanks for your attention. Oh, it's showing there 56 minutes. Am I? Oh, okay.
So you got a minute.
Okay, I've got a couple of minutes. All right. Actually, then let me actually go back. Okay, I'll show.
So this is sort of the horse and the nail and the horseshoe. And the war got lost if you don't use the right nail. I mean,
yeah,
it really is.
yeah.
I love this.
See, I'll just, again, I'm mostly deal in wind, so I'm not as familiar with these, but this is a really kind of groundbreaking study. Let me see, let me go back one more. All right. And then here. So again, 10-story building in full scale, glulam, CLT, composite system out at the UC San Diego facility, putting full scale, simulating the Northridge earthquake, simulating an earthquake from Taiwan, I believe it was, one of the strong ones there. Which one? Yeah, like a 7.6 or somewhere around there in terms of magnitude. And this has just been done a few months ago that they did this testing, and again, worked great, passed with flying colors.
I think the interesting thing about this one is they did like 80 different shapes.
Yeah.
And it's the same structure.
Mhm.
So it not only got
Yeah.
shook one time,
Yeah.
it got shook like multiple times over months.
Yeah, so they basically did the Northridge earthquake, and then right afterwards just went into another earthquake, not repairing it, not restraining, just went straight into another one, still performed just fine. So there's lots of ways that wood. There's sort of this misconception out there that if we build in wood, we're sacrificing strength or we're sacrificing resiliency. Absolutely not. Okay, it's not a trade-off between sustainability and resiliency. We can have both. Yeah. On the exterior cladding and so on. Yeah. So in this case, they focus mainly on the main structure. But you can use curtain walls, any other type of approach. You just have to focus on the connection between those and make sure there's enough ductility between those outer components and your actual structure itself. Because yeah, it's going to move, and you may know a little bit more about that than me actually.
Curtain
Yeah.
facade that has in the first floor.
Yeah, there's 2 stories or 3 stories of curtain wall.
Yeah, and I don't know if it showed on
It showed on the bigger picture.
the bigger picture. Let's go back.
So down at the bottom.
Yeah, I think here in a second there'll be another view that shows.
Yeah.
Yeah. And so they could extend this all the way up as well. I think, yeah, there you go. You can see it there.
And I don't think a single window broke.
No, they did have, I didn't include all of it here because I was, again, wanted to make sure I could finish in time, but they have video from the inside showing, the dining room and everything all, shaking and falling apart. And even in the previous one that I showed at the shake table here, you can see on the inside furniture and everything flying all around. I mean, this is a serious earthquake, and the structure itself performs admirably. And again, it's light wood frame construction. Yeah, the IBH. Yeah, let's go back to the IBHS one as well. The wind one. Yeah, so this is, how many of you had heard of the IBHS facility before? Okay, a few of you. So not far away from you guys at all. Richburg, South Carolina. I don't know if I can, let's see. Yes. Yep. Yeah, so if you notice, pay attention here at the beginning as it plays. So right down here, you'll notice the door pops open. And what happens now? Now the air is entering the building. It's like a balloon filling it from the inside. And now if you think about your loads, you still have the same exterior loads, but now your internal pressure is actually adding to those loads and blowing out the walls, pushing up on the roof, collapsing the structure. And so that's why a lot of I didn't talk about it as much here because I was focused more on the wood aspect of it, but protecting our openings, it really is one of the keys to resilient wind construction. Things like your garage doors and windows and doors, because we design the building assuming that they're all going to stay intact. So the moment they break, now we've increased our loads much beyond what we designed for, and we get these premature failures. Yeah. So this was the one on the left was using typical kind of toenail construction, just nails, basically all nailed connections. So nails between the stud walls and the subfloor, not as many nails in the sheathing, things like that. The one on the right is strapping the roof to the wall, strapping the wall to the foundation, and providing that continuous load path. This was actually a different test they did a little bit later, and they basically braced the door to prevent the door from blowing in, and then the entire roof came off instead. And that's where you don't want to be in front of that camera. Okay, so these are great. These are expensive tests to do. They don't do a whole lot of these, but they're great visualizations of being able to see just what, really a couple $1,000s at most in material and labor, what a big difference that makes in the performance during an extreme wind event.
So you talked about like the weak link being often what causes a lot of the damage here. Is there a way to understand where that weak link might be before an event like this? I'm thinking about like my house right now. I figure out if I've got a weak link, what I can do to fix it.
Yeah, and I think, okay, yeah. So the question was, post, hindsight's always 20/20, right? We can go in after the fact and say, okay, well, here's the weak link and there's the weak link. Can we do that beforehand? And that's really, probably half and half part of the effort that we're doing here with this sort of comprehensive load path assessment is being able to show, well, what is the benefit of switching from a circular washer, a round washer to a square washer? Okay, that makes a huge difference. Don't wait till after the event. Just, we can now point to that as, okay, this causally is one of the factors that's driving it. Now let's fix it in current construction as well. The challenge is, and a lot of times if a home's already built, a lot of that is already covered up. You don't really know what's behind your wall, what's connected to the foundation. You usually have a little bit better access to the attic to be able to see maybe what your roof to wall connections are. But the ones I highlighted really are the ones that I see over and over again. And that is the separation between the upper and lower top plates, because they'll use an 8-foot sheathing panel. The 8-foot sheathing panel just goes up to the lower of the top plates. And then you have an H2.5 that connects to the upper one. And they just sort of overlook that link in between, which is just a very prescriptive kind of a few nails here and there to kind of tie those top plates together. And so you have weak links like that. The sheathing kind of overdriving the nails, that may be something that you're using a lot of missed nails. That's something if you can't, if you're buying a home already as is, but if you replace the roof, that's something you can look for and try to fix before it gets too late. So that garage door is another one. And the garage door, again, that could be a whole other topic, but not just the garage door itself, but a lot of times they'll have the framing. We see this in Florida, unfortunately, far too often, where they'll use similar to what I showed in the Hurricane Harvey, where that garage door had lots of steel bracing on it. And they'll have that, but then where that whole assembly connects to the wall is just a couple of screws. And so then, yeah, okay, the door is going to hold together, but the whole frame just blows into the garage. So it's being just a detail-oriented engineer, thinking through that entire load path and not just focusing on, okay, well, we got a hurricane clip, so we're all good.
So a double door, and this you can't figure out, because I'm just telling you, I actually held a double door closed with a microburst. We lost the roof, and now I feel stupid for standing there holding the door. But at least I think it kept my house from collapsing.
Good.
But a double door, old-fashioned double doors, they might have one, the non-opening door. There was a little tiny brass thing that went in the floor this far. And if you didn't watch it, it would pop out. So don't buy houses with double doors without knowing that they're going to stay in place, because doors especially double
Mhm.
doors. There's no structure unless it's going up and down. Oh, that's a scary thought to
Yeah,
me now, because
yeah.
I would never.
Yeah. Yeah.
Thank you for your presentation. This is all really great.
Thank
What, within your work, how do you get this information out and in the laps of building inspectors, code officials, folks that are actually doing these checks, working with the codes and making sure that there's compliance?
Yeah. Yeah, no, that's a great question, and that's what we're shifting to now. We've done a little bit of that. So we've done some presentations for like local home builder associations. We've done some of that, and then we also work with like the National Weather Service, Department of Emergency Management. We'll do presentations for them, and then they take our material and share it on social media and share it in those ways. But as part of my career project now, one of the things I'm really interested in doing, or we're working on developing, is actually we kind of termed it a views platform. It's visualizing impacts of extreme winds, where we basically can show, here's what it looked like before the storm. Here's some details of it, maybe some hot spots that you can pick at and say, okay, here's what the connection looked like and so on. What do you think is going to happen to it afterwards? And then be able to show people, here's why it performed as it did. And that's all still very much, now that we've got it, we're still not quite there where I want to be on the science, being able to causally say for every structure, okay, here's exactly why it performed. But I think we know enough now that we can build lots of good case studies. And so we're trying to populate some things like that. So it's, it's sort of a shotgun right now of different ways, but it's something we need to work on a little bit more even. Yeah.
Back at the beginning, you showed the probability of failure of different wind speeds,
Mhm.
tornado versus hurricane.
Yeah.
And I was curious, for the same wind speed, failures are much more likely for tornadoes.
Yeah. So there's,
I was wondering if you had any insights on that.
okay, so the question is, when I showed the basically empirical fragility functions that we'd call them, I go all the way back here, and for tornadoes, so for the same wind speed, pick 60 meters per second or so, we've got a lot more damage in tornadoes than we do in hurricanes. So there's two things about that. One is most of our tornadoes happen in areas of the country, like I showed in the wind map. They're designing for 105 miles an hour. Sorry, this is in meters per second. So we're designing for let's say 45 meters per second. 60 meter per second tornado occurs, we're beyond capacity. We're beyond the design levels. Whereas in a lot of the hurricane, we're designing for 60, 70 meter per second as our design wind speed. And so there's just a higher threshold to design. So that's one aspect. That's sort of the easy answer. The second one is a little bit more nuanced, and that is that these wind speed estimates, how do we estimate wind speeds in tornadoes? We estimate wind speeds based on damage. And so these are basically some smooth kind of parametric models of the wind speed, but there's still wind speeds that are indirectly based on damage. And so this is the best that we have for now, but this is something that we're trying to improve on, is basically, in tornado or in hurricanes, we have a much better idea of what the actual wind speed is. In tornadoes, we're kind of guessing at what the wind speed is based on the damage that they cause. So yeah, it makes sense that as we get more damage, there's going to be more winds, the wind speeds are going higher because that's how we estimated the wind speeds to begin with. So there's a little bit of circular reasoning in there. And we tried to do things like tree fall patterns and some, conditioning parametric models. We smooth it some, but at the end of the day, it's still very much dependent upon the damage itself to estimate what the wind speeds are. So yeah, two factors there.
Any other questions? Well, thank you, Dr. Roueche. We appreciate it.